Yes, you can see it.
Okay. Okay. I am Konstantinos Tsioutas, and I come from Athens University of Economics and Business, and I will present you some.
Excuse me,
Yes?
you are showing the presenter view.
Okay.
Maybe it's not what was intentioned.
Do you have two screens?
Okay. It's the same thing? Yes,
No.
same thing.
No, switch to single screen or something.
Just a moment.
Okay. Okay, start the presentation, and on top left you can switch the views. Go in PowerPoint. Start the presentation with PowerPoint. No, it's in editor mode.
Nothing, just a moment.
Start the diaporama.
Okay. Just stop share. Okay, let's again. And I will hold the screen. Share. Better now?
No, on top left, stay like this. Display settings. Display settings.
Yeah.
Click.
Yeah.
Swap. Yes.
Swap. Okay.
Yeah, that's it.
Okay, so we made some measurements, delay measurements, with the motivation of this last 2 years of pandemic and completely isolation, and where multiple musicians had to teach remotely through their computers, and many things were many lessons were conducted via this web conference tools. Which I measured the delay about them. The basic purpose was network music performance, and if these tools, these web conference tools, can allow musicians to play, because as you all know, the basic problem is the audio delay. All of these tools are optimized for speech and audio quality, so the delays are about 150 milliseconds to 200 milliseconds, and this is acceptable when we speak to each other. But when we come to network music performance, delay needs to be lower than 30 milliseconds one way in order to synchronize. Many of these tools have they have many block stages of audio compression, echo cancellation, noise reduction, etc., and all of this to make audio much better and better and better. But finally, all the stages add more and more delay to the procedure. So I made calculations for Zoom, for Skype, for Google Meet, for Microsoft Teams, Facebook, Zitsi, which Dr. Alexandraki mentioned, and I used the infrastructure and the Zitsi server of the Music Collab project. And I compared these conference tools with Sonobus. Maybe some of you know it. Sonobus is an open source tool based on Juice. It has a very friendly UI, as you can see. You have to download it to install it. You have to use, if you run it on Windows, you have to use Ezio drivers. And when you use Ezio drivers, it performs very nice with ultra low delay. You can configure audio buffer size. You can configure, it uses only PCM audio, uncompressed audio. It doesn't use any compression. And you don't have to configure anything about port forwarding or public IPs, etc. Generally, about all of these tools, you can configure some things about audio. In this table here, I present you what I found about what you can configure about audio, about, for example, Teams. Teams, it has the high fidelity option. You can go to the settings of Teams and use high fidelity option. So it aborts all the stages for speech processing, and it gives you the ability to exchange audio high quality. The same thing uses zoom. You can see it in your interface that you can choose the original sound. I think it's a button on the left. Facebook is not configurable. You cannot do anything, and it uses advanced audio codec, I think, according to the literature. Skype is not non-configurable, as Google Meet too. And Tsioutas, which it's open source, you can do things. You can change some parameters through a config file, or by the URL. There is a documentation how to do that. You disable many through the URL. You disable main configure stages. Finally, the Sonobus I showed you before. Okay, how did I do the tests? This is a LAN configuration here, and let me explain it. Basically, you can see two computers, endpoint 1 and endpoint 2. Basically, I send audio, and I loop back the audio here physically through a cable, through the audio interface. I plug a cable from the headphones to the microphone. Okay, this is a LAN configuration in terms that these endpoints are in the same computer lab. From this laptop, I play audio clicks from Audacity, and I stream them to from the first computer, the endpoint, to reach the second endpoint and come back. I have here a console where I can route the signals, and I make the recordings in the second laptop here, so I calculate the real my mouth to my ear delay, the real two-way delay, one-way, two-way. So by comparing this peaks here, I can calculate how many milliseconds is the round trip delay for audio. At both endpoints, all these applications, I tested all the applications you can see. Of course, Zoom, Teams, Skype, Facebook, Google Meet have somewhere a server. I don't know where the server is. I think I considered all this architecture as a black box, but the two endpoints were in the same lab, in the same room. In a second configuration, in a one configuration, the second endpoint was in my home. This laptop was in my home where I live, behind an ADSL line. Okay, so I had all the setup in the computer lab, which is in the center of Athens, for example, and the other endpoint was in about 8 kilometers distance. This is 8 kilometer distance from here to here. So I streamed audio from this computer to that one through I don't know where. I don't know. I don't have a clue about the audio paths or the packet paths, the internet paths that the audio would travel. The only thing I know that Tsioutas server is located in Heraklion, Crete. So when I used Tsioutas, my audio streams went from Athens in the center to Crete. Then they went to my home in Athens and back through the Tsioutas server. I had to do multiple configurations about avoiding echo cancellation. Echo cancellation is when all the applications use echo cancellation to avoid hearing yourself two times. So when you speak and you are confused. and they have an algorithm to when input signal and output signal in the same application is the same, the two signals. You cannot loop. When you loop back the audio, you don't hear anything. So, for example, I couldn't loop back in this setup the audio when I had Facebook, Google Meet, Skype, and Teams. It was very difficult. To avoid it, I used parallel sessions. For example, I used multiple tabs of the browser and multiple users to log in. So one session, the input from the session from one session goes output to the other session. So that way I could avoid the echo cancellation. It's rather technical, this thing. So we don't have so much time, so I will go to the results. Here you can see the results. The results, Sonobus gave the best audio delay. In this axis here, you can see the delay in seconds, from 0 to 1.2 seconds. Okay, Sonobus performed very nice. In the blue box, you can see the LAN configuration when the two computers were in the same place. Okay, so Sonobus gave about 20 milliseconds two-way, and this delay was from the computer lab to my house and to my home and back. So this difference here is the network delay from the laboratory to my place. All the other tools gave very big delays, with the worst delay for Google Meet. The results are not at all representative, because we made very few measurements for 1-2 days, and we didn't use many repetitions for calculation. So we have to, and we'll do it. We are in these programs, and we are making everyday calculation till them during the morning, the noon, the afternoon, etc., to have a more representative representation of the values. Tsioutas was the best performance for the web conference tools compared to the rest of them. Okay. Generally, all these web conference tools are not suitable for network music performance and for real-time network music performance. And as mentioned in the previous presentations about Musical Lab, one of the components there was the Tsioutas server. Is for real-time, but with delay. And there is a lot of things you have to do to reduce the delay. I watched the first presentation about WebAssembly, and as Dr. Alexandraki has suggested me, WebAssembly maybe is the next step to reduce delay through web browsers and have solutions through the REST browser. There are many tools now at the moment for network music performance: SoundJack and JackTrip and Jamulus and JammerNets. Many of them are open source, but most of them don't operate through the web browser. You have to download an application, set up Xent, install the application, etc. I said about the future work. Thank you very much, and if you have any questions, I will be glad.
Thank you, Costa. We have one question from Michel.
Yes. So, how did you test GT, for example? Because as it's using WebRTC, if you are in the same room, it will be instantaneous or nearly instantaneous. But if you are from different long distance. It depends if it uses a server in the middle or if you manage to get a direct peer-to-peer connection, because the WebRTC protocol is doing lots of things behind the scenes. If you open a VPN, you'll get other results and so on.
Yeah, it's complicated. It's not so clear. I didn't follow the paths and didn't use any Wireshark to track where everything was going. I assume that according to the documentation, when I use two peers, I have a peer-to-peer. So when I did calculations in the lab, I think my packets didn't go out, didn't go outside, didn't go to the server in Crete. I had the path from the one computer to the other, but I cannot confirm that. In the case of more than two users, you don't have a peer-to-peer. You have all the packets going to the server. I have seen in the documentation.
I think you have to configure peer-to-peer to get peer-to-peer in Jitsi.
I had
And he was
configured.
using the server in Crete.
I've been working a lot with WebRTC, so you can have a mesh even with 4 users, but depending on your router or your firewall, it does the deep packet inspection. Sometimes it doesn't let you open a peer-to-peer connection, even on a local network. If you go with the Wi-Fi of the university, you cannot. And then in that case, it uses a turn server. That means a man-in-the-middle server.
Yeah.
And in that case, the latency will be doubled, at least. So this
Yeah.
is why I say with these peer-to-peer tools, you must be very careful when you say they are faster, because it really depends on the way you open the connection.
Okay.
That was just my 2 cents.
Okay. Thank you. Yeah.
I think Jitsi was used with our server in Crete, no?
Yeah. Yeah. Yes.
So it was the signal was going Athens to Crete and then back.
I don't know what
We have our
yeah.
own server.
Yeah.
Okay, this is interesting. I would like to talk about it later. So thank you, Costa. We're running out of time.
I have one more quick comment if you have a chance. That was a
Okay,
really
yes.
cool presentation. I'm wondering, so it does seem like from a latency perspective, part of it may depend on the server distance from where you are. So if you had just a computer in your lab running your custom server, I'm wondering, I know you didn't do this experiment, but it might be cool to look into. You have your own server, I don't know, right next to your office. Would that give you comparable results to Sonobus?
Okay. I have a computer here with Jitsi, which runs Jitsi. Here, it's next to me. And the delay is big.
I mean like the server, because for Jitsi it's still being sent to Crete. But if you have another server that's running, that's doing the relay, I don't know, maybe. I'm also not too familiar with servers, so this could be a bad question.
I'm going to search about it. Okay. But but the machine I have here gives me over 100 milliseconds to hear my sound, to go to the server and come back.
So but you're still sending it to Crete, right, for Jitsi? Because since it's based in Crete, it has to go to Crete, come back to where you are.
I think the 100 milliseconds is without the...
Without
Oh,
Crete.
without the server.
Without Crete.
I have
so
in my
Jitsi's
lab
okay.
also a second server, a second Jitsi server.
Oh, okay, got it.
Okay.